Well, thank you for the introduction. So I will be presenting some early work in progress together with Guilhem in Nantes and Colin Riba at ENS Lyon. And actually, I will come to HOPE'22 at the very end of my talk. And most of the talk will be about motivating what I want to do with temporal refinements and get into troubles, let's say. So first, for a bit of context, what we want to do in this kind of work is to consider some functional programming with co-inductive types, so some kind of functional co-programming. So we have this type of streams that we can describe as a fixed point of either a head or the tail of a stream. And so we consider equi-recursive types. So a stream is isomorphic to its one-step unfolding of its head and the tail. On such stream, we can define higher-order function, for example, the map function that takes a function from A to B, a stream from A, decompose the stream into its head and its tail, apply the function f onto the head, and then continue mapping onto the tail. We also want to consider other kind of infinite data types that are branching, but in a finitary fashion. I will return to that later. And all the work that all this work in progress is based on previous work by Guilhem and Colin on temporal refinement types or guarded recursive types. And the point is that in this talk, I don't want to have a guarded part. I want to consider potentially unguarded fixed points. So what kind of things do I want to do on this kind of programs on co-inductive data types? Well, I want to be able to specify extensional properties of this program. And by extensional, I mean specify the input-output behavior of the program on this infinite data type. And in order to do that, I will use some logic, the model mu calculus, or rather some fragment of the model mu calculus, to specify the properties that I want to my program to satisfy. And so an example of such a property is if we assume a property phi over a type A and a property psi over a type B, then we say a function f from A to B, we will want to be able to specify that if the input satisfies the property phi, the input of type A, then the output f of x satisfies the property psi. And on top of these properties, we'll want to use modalities, such as the eventuality, the diamond modality for eventually the property will be true, or the box modality to say it will always be true. And on a function such as map, we can consider multiple kinds of properties that will hold using this modality. So if we know that the input stream satisfies always eventually the property hold, then mapping with a function f on the stream, with a function f that satisfies the property above, will result into a stream that satisfies a similar property. And we can do the same if we reverse the eventually with the always. And the question is, how do we set up such a system where we can define functions on infinite data types and after the fact prove specifications of properties on top of this function that already exist? So the problem in general is undecidable. So it was shown by Kobayashi and co-authors in 2010 that if we take as a programming language the simply type lambda calculus with fixed points and restricting to finitary data type, then we can restrict the problem of the inference of such of checking such properties for an arbitrary program to, if I remember correctly, they reduce the problem to some problem in automata theory, which is shown to be undecidable. So here in this talk, we'll take an approach which is not automatic. We don't want to just specify the thing and say, okay, does it hold or not? will go toward a type system to describe the base programs, and then a logic on top of these programs. And we'll show the correctness of our approach through denotational semantics. So let me explain a bit how we will do that in more details. Well, we'll consider a simply typed language with a fixed point. I won't go too much into the details of what kind of language I want to consider in this talk. Just think simply typed lambda calculus, a combinator for fixed point, recursive type in order to have infinite data types. And on top of this language for programs, we'll add refinement types to specify when program satisfy some specification. And we'll have, of course, some subtyping rule that goes with these refinement types. And the important point is that we want to be able to give multiple refinement types to the same function, in the sense that we don't want the refinement to be something intrinsic to a function, but rather something that we can prove after the fact on the underlying implementation. So here I take again the two examples of if I have a function that maps type A that satisfies phi to type B that satisfies psi, then I can prove similar kind of properties on the stream by adding modalities. So let me maybe detail a bit more what kind of properties we want to have on this, what kind of refinement we'll give on this data type. So I say that we would use formula from the model calculus. So it means the standard propositional logic plus two fixed point combinator, mu and nu, for smallest and greatest fixed point. And I will also add at the level of specification, modalities that correspond to the action of programs on properties. So for example, if I have a property phi that holds on a type AI, then projecting onto the I component allows me to pull back that specification to the product A0 times A1. And if I have a property phi that holds for the one-step unfolding of a recursive data type A, so here I have A where I unfolded the variable x by the fixed point, then I can get formula on the folded version by using this modality fold. Using this kind of modalities, we can then develop over higher level modalities. For example, on streams, I can define a modality later that will have the rule that whenever I have a stream that starts with a head and a tail, if the tail satisfies the property phi, then the whole stream where I added a head satisfies the property later phi. And this property later phi is just defined as a composition of fold with the projection. I can also do a similar thing for the head. If I have, in order for a stream to satisfy the property head of phi, it's enough to have an element that satisfies the property phi, and I define the modality head as a composition of fold and projection. So now, I said at the very beginning that the main change that I wanted to do in this talk with respect to previous work was the fact that previous work were considering guarded recursion. And in this work, I don't want to consider guarded recursion, I want to consider arbitrary fixpoint. Why is it the case? It's because I want to consider functions such as filter that take an input stream and a Boolean predicate P, and that goes through the stream, keeping only the elements that satisfy the predicate. The main problem with this filter function is that it's not necessarily productive. If you take a predicate that's always false, it will just discard every element and never return an actual result. And that's one limitation that existed in previous work considering only guarded recursion, which is that the language itself was syntactically ensuring productivity, And so you couldn't define this function, at least not literally, as I described it here. And even if this function is not productive, we can still at least define it in an expressive enough language when we have arbitrary fixed point. And on top of this definition, we can show actually that under the right hypothesis, this function is actually productive. So the kind of right hypothesis that we can have is if the input stream, if we have a property phi that corresponds to the Boolean predicate P, and we know that the input stream always eventually satisfies this property phi, then we can just keep all these. Since we know that there is infinitely many elements that satisfy the property, we will be able to return all these elements by searching from them. And in a similar fashion, if we know that eventually, ultimately, all the strings satisfy the property phi, then filter will also return some actual result. So that's all the motivation. Now let's go maybe in a bit more details about the kind of properties that I want to be able to show. So I said that I wanted to have modalities in order to specify my programs. And this means that there is two classes of properties that I'm interested in. The first class are safety properties. So safety properties are properties that state that a bad event never occurs. And so one important point is that on streams, if we consider the Scott topology on these streams, they correspond to closed subsets. And they also correspond to formula of shape box of another formula. And here we can actually define box, the modality box, using a greatest fixed point and the later modality that I presented before. So I don't need to take box as a primitive. I'm just defining on top of this mu calculus fragment that I have. And how do we work with such safety properties? Well, we take inspiration from Colin, and our greatest fixed point is, it is a fixed point first. So if we have the greatest fixed point of phi, I can unfold it. And if I have that the unfolding hold if I have a coalgebra basically for this phi formula that is parameterized by the variable alpha, then I know that psi entails the greatest fixed point. And in terms of refinement, it means that on streams I can derive rules such as this one. In order for a stream to satisfy always phi, then I need to have that the head satisfies phi and the tail satisfies always phi. And then on map, I can show that if I have a function that sends phi to psi, then always a stream that satisfies always phi is mapped to a stream that satisfies always psi. The second class of property that I'm interested in are liveness properties. And liveness properties says kind of a dual of safety properties in the sense that something good will happen at some point. Another time, this time again, we can look at the topological meaning with the Scott topology on streams of this class of property, and they correspond to dense subsets. And we can syntactically see them as formula of the form eventually some formula. This time again, we can define this eventually modality using only smallest fixed point and the later modality on streams. We can give rules for this smallest fixed point using another time the rules from Colin. So it's exactly the dual from what I gave for the greatest fixed point. It's a smallest fixed point, so it's entailed by its unfolding. And if I have an algebra, if psi is an algebra for the phi transformer, then the smallest fixed point entails psi. And finally, on stream, I can give two rules to introduce this eventuality modality. The first rule is saying that if the head satisfies phi, then the whole stream satisfies eventually phi. And the second rule is saying that if the tail satisfies eventually phi, then the whole stream satisfies eventually phi. Now, we need to be a bit careful with this kind of eventuality modality, in the sense that if I take an unrestricted rule to specify fixed point, I might very well get into troubles. So for example, if I say that for specifying a program that uses an arbitrary fixed point, it's enough to show that under the assumption that its recursive call satisfies the fixed point, the whole thing needs to satisfy the fixed point, then I will be able to show that the stream that infinitely often, that only produces false, the Boolean stream that only produces false, actually satisfies the specification eventually true. So here, this would be a problem if we don't pay enough attention to the rule that we give for fix. And this corresponds to the fact that if we take a denotational point of view and we interpret all our programs, possibly non-terminating program, as domains, and we try to look at a rule for fix, then the natural way to interpret a rule for fixed point is Scott induction. And Scott induction has an important side condition, is that it only applies to closed subset for the Scott topology. In particular, this means that I won't be able to prove liveness properties, which are dense subset, unless they are trivial, because they need to be both closed and dense. So let me try to give you a picture of an ideal solution that is kind of a transposition of what happened in previous work. So the same kind of problem between liveness properties and safety properties happened already in the setting of guarded recursion. And here I would like to be able to just take the result from my co-authors and transport it to basically domain theory. So let's assume that I have some domain D that interpret my programming language with non-termination. And I want to have two points of view. The point of view of the model itself and an external point of view that I take in sets, where I will be able to take some kind of extrinsic view at streams. Actually seeing streams as infinite sequences of Booleans and being able to specify properties on these streams through arbitrary subsets rather than just closed subsets of a domain. So here, I take D to be a category of domain, an arbitrary one with Scott continuous functions. And so as I was saying, on the left side, we have fixed points and Scott induction, basically. On the right, it's sets and functions, and it corresponds to the usual semantics for liveness. And the functor that I have on the top, gamma, is the underlying functor. And in order for the whole thing to work, I need to have an adjoint to this underlying functor. So if, let's suppose for a second that I'm able to have such an adjunction, then I'm claiming that I will be able to solve the problem that I have with respect to safety and liveness. Let's see how it goes. Well, basically, from this adjunction, I can build a comonad on my category of domains, which is this black box. And on this comonad, I will be able to specify properties on domains as if they were in the set world, meaning that I will add a new modality box on properties that says that if I have a property that holds for A, then I can lift it to the comonad. And I will add a refinement of this comonadic, of the comonad applied to A that allows me to talk on the domain side of the subset presentation of specification. In particular, what it means is that under such a box, the liveness properties will have the correct interpretation in the usual sense of the term. Whereas if I was using them on the domain side, they would have a non-standard interpretation that would basically occupy the whole space. And in order to work with this box, I introduced two rules. If I have a program M that satisfies A such that phi, then the box of M satisfies square box of A such that the box property. And I have an unboxing rule with a side condition. The unboxing only works if I consider a formula that is called safe. And what does it mean to be safe? Well, being safe is actually a purely semantic condition. It means that my interpretation on the domain side and on the set side will actually coincide. So it means that in the case where the things actually coincide, well, I can go back from the set world to the domain world. And in order to, this restriction could be seen as extremely restrictive. In particular, as I'm saying, like diamond, so a safe formula will in general not involve any diamond, no safety properties. And so that could be a problem to be able to mix diamonds and squares in our specification. But we can actually realize that the fixed point that specifies the diamond property is alternation free. And because of that, we can approximate any diamond through a sequential suprema of later, iterated laters of that formula. And then if we truncate that formula to any finite amount, it will preserve the safety of the base formula, meaning that whenever phi is safe, then the finite truncation of this diamond will be also safe. And so one way to go around the limitation for having this rule only for safe formula is actually to be able to do finite approximation of all our safety properties and to make the system, the whole logic, much more indexed by this kind of finite approximation so that we can prove more things. So I will not get too much into this kind of details. This is much of an idea from the previous work, but that was just to say that the expressivity is not at risk here, but we can actually specify things that mix diamonds and boxes. Now, let's return to one hypothesis that I took at some point. But I said we need an adjunction between a category of domain and a category of set where my right adjoint is the underlying set functor. Well, I say that in order to interpret non-trivial fixed point, I need D to admit non-strict function. Well, I didn't say that, but I'm saying it now. D must admit non-strict function, and it must have at least one, each element, each type, each domain must have a least element. Why is it the case? Basically, because the way to interpret fixed point is to start from the bottom element and then to iterate the function up to the smallest fixed point. And if we have only strict functions, then the only fixed point that we'll have will be the bottom element. So that's why we want these two conditions. And now, if we consider any domain C with an element which is not bottom and any set that is non-empty, we can consider the function from this set X to the underlying set of C. And this function actually has two distinct lifts. So you can either lift it with a constant function, or you can lift it by the function that matches whether the input is a bottom element or not. And these two functions are distinct. So actually what this means is that the ideal situation that I pictured above cannot exist. I cannot have an adjoint to the underlying functor of from a domain category. So what should I do? Well, that's where...
You should wrap up soon.
Perfect. I should wrap up. So basically, there is a great solution, which is to invoke Paul Blaine-Levy and to transform this domain category by a model of call by push value. Instead of having one domain category, I will have two categories of domains. one with directed CPOs, and the other one with directed CPOs, but without bottom element and strict functions. And separating my category of domain into two allows me to split the problem that I had before into two parts. Plus, I can still define fixed point, because fixed points are not defined in one of the two categories, but as oblique morphism of the adjunction on the left. So on top of this pair of adjunction, I can consider the subobject hyperdoctrines. And actually, because all my adjunctions, all the functors in my adjunctions preserves monos, then I will be able to lift that adjunction to these hyperdoctrines. And actually, this is a point where up to where we got a work in progress, let's say. And we have ideas to try to go further, like adding other effects, trying to see what it would give in a setting of guarded recursion by considering an explicit lift delay monad, or trying to look at dependent types. But I guess this will wait for another day.
All right, let's thank the speaker.